Hey guys, welcome to Computer Organization. So this course will be good for computer science majors, computer engineering majors, and electrical engineering majors. So the point of this course is just to teach you about the computer, what's inside the computer, the different types of memories, the way um, data passes throughout the computer, or as well as just hardware pieces inside, like the processor, control unit, ALU, and different data buses. It's just an overall computing course for computer related majors. So, what we usually like to talk first is what is the difference between computer organization and computer architecture. Computer organization encompasses all physical aspects of the computer. It focuses on circuit design, control signals, and memory types. So, how are these circuits designed? What different types of memory we want to include, like high level and more expensive memory, such as cache, which is much closer to the CPU, and how much RAM that we want to have, and hard drive. There's different types of memory used for different types of things, and how expensive they are, and why we use some different types of memory sparingly compared to others. So the question computer organization asks is, how does a computer work? But the difference with computer architecture is it's the logical and abstract of a system that is seen by a programmer. So this types of stuff is like instruction sets, formats, data types, addressing modes, memory access modes, and IO mechanisms, which is just the input output mechanisms, how a computer is receiving input and what it's outputting. So the question computer architecture asks is, how do I design a computer? But there's not really a clear distinction between these two, computer organization and computer architecture. So one thing we do want to make clear is the law of principle of equivalence of hardware and software. Any task can be done by software, can also be done using hardware, and any operation performed directly by hardware can be done using software if speed is not taken into account. There's a differences in speed between these different sections between hardware and software. So, uh, since this is an introductory video, we're going to be looking at the introduction into computers, starting out with mechanical calculating machines, known as Generation Zero. The first one is the calculating clock, which is created by Wilhelm Schnickert. It's the first mechanical calculator, and this device could add and subtract six-digit numbers with a bell for a seventh digit that deals with overflow. And we will definitely talk about overflow, especially when you're doing binary addition and subtraction. And it was used using six different interlocking gears. The second one, which was 1623 through 1622, was the Pascaline, and it was created by Blaise Pascal. And this focused on addition with carry and subtraction. It was also called the arithmetic machine. It was actually the first calculator and machine to be produced in quantity and actually used. So the third calculating machine that we have is the difference engine, created by Charles Babbage. But he also designed the analytical engine, but he never created it. The difference engine was based on calculating technique called method difference. There's no reason to know that. We're just doing an introduction and just a brief overview of all these. And the analytical engine included several components, and it was associated with modern computers. It had an arithmetic processing unit to perform calculations, memory, and input output devices, and it was the father of computing. The reason that we say the father of computing is because most modern computers, or just the definition of a computer, is that it has to have some form of uh, to have some perform some arithmetic and logical operations and bitwise operations, which is usually performed by the ALU. It needs to have some type of memory, uh, RAM, cache, hard drive, or it also needs input and output mechanisms. And the last mechanical machine that we talk about is obviously the punch card machine. We all know what the punch card machine is, and it was used well into the 1970s. And for the first generations of computers, we use vacuum tube computers. The first computer was the ABC, and this computer was created in the 1937s and 38s. And this computer solved systems of linear equations, and it was the first completely electronic computer. So the way it worked, it used thermionic emission. It pretty much says it's the fall of electrons from negatively charged cathode to positively charged anode. There's no reason to know this. We're just going through the generations of computers. And the ENIAC was the first all electrical and general purpose computer, and it was created in it was founded in the 1946 at the University of Pennsylvania, and the IBM 650 was the first mass-produced computer, and it was phased out in 1969. So the second generation, the transistorized computers, this is when we see a huge shift in computers. If you are an electrical engineering student, or a computer engineering student, or even a computer science student, you will have heard of a transistor. A transistor is a semiconductor device, and it's used to amplify or switch these electronic signals and electrical power to deal with power in a system or in a circuit. So the thing is, the vacuum tubes were not very dependable. They're very easy to break, or there was not enough gas in them, or just very different problems. Transistors consumed less power than the vacuum tubes. They were smaller and they work more reliably. And on top of that, you can have more transistors. That's when we get into integrated circuit chips. So the third generation is the integrated circuit computers. This is when multiple transistors were integrated into one chip, and these are the different types of third generation computers that they had back in the 1960s to 80s. And so the fourth generation VLSI computer is still used today. So what these are, they're very large scale integrated circuits, and they have more than 10,000 components per chip. And up to now, there are actually ultra large scale integrated circuits. There's still a family of the VLSI, but they include millions and millions of transistors in one chip. And the first VLSI was the 4-bit Intel 4004. And there were, of course, later versions that spawned the idea of personal computing. So here is a chart of the computer evolution, and as you can see, these continue to evolve, increase capacity and performance, and reduce costs. So like we said, the first ones were the vacuum tube, then came the transistor, then came the integrated circuit, and then the VLSI, and now the Ultra LSI. And this is just, like I said, it's a subset of the VLSI. So as you can see, the relative performance to cost. So this is when we get to a part in this section. It's called Moore's Law. Moore's Law pretty much states is that the density of transistors in an integrated circuit will double every single year. That was back in 1965, so a contemporary version is saying that the density of silicon chips doubles every 18 months. But it can't double. This law cannot hold forever. So Rock's law, which is the opposite, which is the counterpart, I wouldn't say opposite, counterpart law, is Arthur Rock. He said that the cost of capital equipment to build semiconductors will double every 4 years. So, in 1968, a new chip plant cost $12,000. And that $12,000 was a nice house. In 2012, a chip plant under construction costs well over $5 billion. So, for Moore's Law to hold, Rock's Law must fall or vice versa. What it's saying is if this density of silicon chips doubles every 18 months, but the cost of capital equipment to build these silicon chips will double every 4 years. At some point, the cost will be way too expensive for us to keep doubling the chips, the chips in our computers, because at that point, costs would be skyrocketed, and these users would see no us as a consumer, we would see no reason why to buy this computer for it to be only a little bit faster for this so much extra more money. So at one point, one of these laws have to stop. It's either Moore's law or vice versa, Rock's law. So what is a modern computer? A modern computer is an electronical, digital, and general purpose computing machine that automatically follows a step by step list of instructions to solve a problem. And this list can either be an algorithm or it could be a computer program. So there is different types of steps. It's called the fetch, decode, execute cycle, which we will see in the next video. But there is instructions that the computer has to follow in order to execute these instructions. So, at the most basic level, there's three computer components. There is a computer processor to interpret and execute programs. There's a memory to store both data and programs. And there's supposed to be a mechanism for data input and output. So, this is when we get into the course of measures of capacity and speed. So, typical measures of capacity that we have in computers are the kilobytes, megabytes, gigabytes, and terabytes. So, for the kilobytes, or kilo, it's 10 to the third. But when we're talking about computers, we're talking about to the power of 2. And why are we talking about the power of 2? Is because computers only deal with zeros and ones. There's only two options that you can do. So a kilobyte is 2 to the 10 or 1024 bytes. Mega is the same thing. In a power of 10 is 10 to the 6, but in powers of 2, it's 2 to the 20. In giga, it's 2 to the 30. In tera, 2 to the 40. We don't really need any of these. And typical measures of speed, it's kilobytes per second, megabytes per second, gigabytes per second, megahertz, and gigahertz. So measures of processor speed and storage. So a byte is a unit of storage, and it's usually composed of 8 bits, zeros or ones. A 0 is 1 bit, a 1 is 1 bit. So this is a byte. So 0, 1, 1, 1, 0, 1, 1. So this is a byte right here. It's composed of 8 bits. And these 8 bits combine to do, it says some instruction. It calls for some instruction. It can be anything. It just really depends on what the computer is talking about. So what a kilobyte is, it's 2 to the 10. This is the power of 2. It's 2 to the 10. So once we do the 2 to the 10, it's going to be 10,024. But for power of 2, that's why we have this bytes right here. So 2 to the 10 is 1,024 bytes. Or megabyte is 2 to the 20, or this many bytes. And of course we can keep going on for gigabyte and terabyte. And then here we have main memory is measured in gigabytes. Main memory is RAM. It's random access memory. It's memory that can be read and changed in any order, and it's used to store working data in machine code. It does not store data permanently. That's what your hard drive does. Your random access memory, it's all the tabs in your computer. For example, let's say you open a browser and you have 15 tabs open. Why does your computer start slowing down? Because you have so many tabs. Because that's all being held on your RAM. And once you have so many tabs open, your RAM is becoming more filled and more filled and more filled, and it's becoming slower. So that's why usually RAM is really good for gaming because it can hold a lot more memory. It can load games faster, or it can be good for web pages, videos. Um, it stores the working memory. So what happens with RAM? What happens when you call a program? Let's say you call Microsoft Word, one of your files, right? So your computer goes to your hard drive. It finds a copy of that Microsoft Word or that essay you're doing, that PowerPoint that you're doing, and it copies it into your RAM, and you're changing it on your RAM. You're working this on your RAM, and once you save this, a copy is put back into your hard drive. That, in layman's term, is what's actually happening. But of course, it's a little bit more complicated than that. But in layman's terms, that's what's happening. Your RAM is where you're working on, and your hard drive is looked as more of a permanent storage. And that's why you can have so much more memory on your hard drive, and it costs less. The RAM, it needs to be faster. Uh, it needs to be working continuously. So for this storage, it's usually measured in gigabytes for small systems and terabytes for large systems. RAM is usually only measured in gigabytes, and it's a lot less than in disk storage. So when it comes to your processor, the processor speeds are measured in megahertz or gigahertz, which is just talking about clock cycles per second. All right, so here's the measures of time and space. Typical measures of time and space: milliseconds, microseconds, nanoseconds, pico. You don't really have to go to these; they're just showing you more. So milli is 10 to the third, micros 10 to the sixth, nanos 10 to the ninth, picos 10 to the 12th. And here's showing in powers of 2, just exactly like it was doing it before. And you can use the same thing for measures of space. So 1 millisecond is 1,000th of a second. So 1 second equals 1,000 milliseconds. So the hard drive disk, it takes about 10 to 20 milliseconds, and it's actually the slowest of your memory. So cache, which is the closest to your processor, has the fastest memory access time. Then there's RAM, which has the other. There's different levels of cache as well. There's like a level 1, a level 2. Then there's RAM. It really depends on the type of system or computer that we're talking about. And of course, the cache, since it has the fastest access time, it's the most expensive, and it has the least amount of memory. Then it comes to RAM, which is what you're working on, the storing. And then we have the hard drive, which is what's doing the permanent storage on your computer. Then we have a nanosecond. So 1 second is 10 to the 9 seconds. Nanoseconds. So main memory access, which is your RAM, have about 50 to 70 nanoseconds. As you can see, it's larger than this one. This one's about 10 to 20 milliseconds, and this one's 50 to 70 nanoseconds. And here's just an example of a space, a micrometer. It's a 1 millionth of a meter. So circuits on computer chips are measured in microns. So thank you guys. This is the end of the first video. We are definitely gonna look into how to, you know, work with these types of measurements and how to convert from seconds to milliseconds, nanoseconds to microseconds, that type of stuff. This was only an introductory video on computer organization. I promise you this course will get much harder. We will be talking about, in the future, we will be talking about octo, hex, bitwise. We're going to talk about adding, subtracting bits. So we're going to be talking about complement, two's complement of bits, how the computer talks, how negative numbers look in bitwise function, not bitwise function, in bit operations, or how in complements. So there's going to be a lot to this course, and I'm following a college curriculum on this course. So nothing that you're everything that you're seeing is what I saw in my college course. So please stay tuned. We're gonna have a lot of time and a lot of fun trying to get through this course together. Well, thank you so much, guys.